In this video, we're going to continue talking about polynomials and rational functions, but we're going to use them in solving inequalities rather than solving equations. So we've solved inequalities before, but they've always involved just linear functions. Now we're going to have higher exponents in our inequalities, and we're even going to use rational functions. So it gets a lot more complicated, but there's still just a set procedure to use, and it ends up not being too bad. So let's start with the definition. We're going to let f of x be a polynomial. Then, an inequality of the form f of x is greater than 0, f of x is less than 0, f of x is greater than or equal to 0, or f of x is less than or equal to 0 is a polynomial inequality. So to solve a polynomial inequality, you're going to start like it's an equation. So it's important to make sure you have a 0 on one side of your inequality, and then first solve it as if it was equal to 0. Find the numbers that make that polynomial 0. Then we're going to test points on the number line in each of the intervals separated by those boundary points to check to see if our inequality is true or not. So let's do some examples solving a polynomial inequality. So example, let's solve 2x times x minus 1 is less than 21 minus x. And now the first thing I'm going to point out is this is a polynomial somewhere, and there is an inequality, but it's not in the correct form yet. We need to rewrite this so that we have a 0 on one side of this inequality. So first thing I'm going to do is distribute on this left side to get 2x squared minus 2x, and I still have 21 minus x on the right side. I'm going to move everything over to this left side. So I'm going to add x to both sides. And then I'm going to subtract 21 from both sides. So now I have the inequality in the correct form. I have it less than 0. To solve this, the first thing we have to do is pretend that this is an equal sign instead of a less than sign. So the first thing you do is solve the related polynomial equation. And to solve this, we're going to factor. So I'm looking for two numbers that multiply to 2 times negative 21, that's negative 42, and that add up to my b, which is negative 1. The numbers that do that are negative 7 and positive 6. So I'm going to split up that middle term using those numbers. And then factor by grouping. So in my first group, I have an x in common. And in my second group, I have a 3 in common. So then this factors as 2x minus 7 times x plus 3. Using my zero product property, set each piece equal to 0. And I get x is 7 over 2, where x is negative 3. Those are the two values where I'm equal to 0. But what we actually want to find is where our polynomial is less than 0. So to solve this, I suggest you make a number line just to help you organize your information. It does not need to be a perfect number line. your two numbers that we just got here on the number line. The important thing is that we know -3 is to the left of 7/2. And now notice when I put my zeros on this number line, it divided my number line up into pieces. I'm going to test a value in each piece to see if my polynomial is positive or negative. So over on this side, I'm going to just check what I get when I use a -4. In the middle, I'm going to use 0, just because that's the easiest number I can think of. And 7/2, that's 3.5. So on this side, I guess I'll use 4. It does not matter what numbers you choose, as long as you're choosing one from each piece. So pick the easiest ones you can think of to work with. So let me rewrite what my polynomial was. And I'm going to do it in the factored form, because that's all that we really need. So here was my factored form of my polynomial. And I don't even really care what the number ends up being. I just care if it ends up being positive or negative. So let's first think if I plug in -4. I would have 2 times -4 minus 7 times -4 plus 3. Now this right here, 2 times -4 is -8. Minus 7 is even more negative. This is negative. -4 plus 3 is also negative. A negative times a negative is positive. So I know in this section of my number line, I get something positive, something greater than 0. We're going to do the same thing with 0 and 4. And I'm going to do 4 first, just because then I can just erase a little bit. There. If I plug in 4, 2 times 4 is 8, minus 7 is positive. 4 plus 3 is positive. Positive times positive is positive. So over in that section, I'm also greater than 0. Now let's see what happens if I plug in 0. So if I plug in 0 everywhere, 2 times 0 is 0, minus 7 is negative. 0 plus 3 is positive. Negative times positive is negative. Now we have to remember, were we solving greater than 0 or less than 0? And it was less than 0. So I want the section of the number line where I get negative results. And since it was less than 0, not less than or equal to 0, I do not include the endpoints. So the answer to my inequality is the interval. So in interval notation, we get -3 to positive 7/2 without including the endpoints. Those are the values that made that original inequality true. And that's all there is to it. So first you treat it like an equation and find the zeros. Then you plot them on a number line and check something in each place on the number line. And you don't need to even find out what the exact values are. You just need to find out if it's positive or negative. That's it. Let's do another example. All right, so I have x to the 4th minus 18x is greater than or equal to 3x squared minus 4x cubed. And remember, to solve these polynomial inequalities, you want a 0 on one side. So I'm going to move these guys over to the left. That will get me x to the 4th minus or plus 4x to the 3rd minus 3x squared minus 18x is greater than or equal to 0. And I'm going to start by factoring this. I see that there's an x in common for all of them. But now I'm a little bit stuck. I have to keep factoring this to solve when this is equal to 0. But luckily, we know all about how to find all of our zeros. Let's start by just listing all of the possible rational zeros that we have. So the possible rational zeros that we have are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18 by using our rational roots theorem. That's a lot of different roots to check, and we're not going to check all of them right now because we don't want to do the same video for like 5 hours. So I'm going to tell you right now that after checking a few of these, x equals 2 ends up being a root. So then we have to keep factoring this. We know x equals 2 is a root, so that means x minus 2 is a factor. But then what's the other factor look like? Well, to figure that out, let's just use some synthetic division. My coefficients were 1, 4, negative 3, and negative 18, and I'm dividing by x minus 2. Drop down the 1, multiply, add, multiply, add, multiply, and add. We got a remainder of 0 like we were expecting, because remember, we already knew this was a 0. So this tells me that I already had an x, I now know I have x minus 2, and my other factor comes from this work right here. I have 1x squared plus 6x plus 9. And all of this is greater than or equal to 0. So it's still not fully factored. But this x squared plus 6x plus 9, two numbers that multiply to 9 and add to 6 are positive 3 and positive 3. So I have x minus 2. This would be x plus 3 times x plus 3. So that's x plus 3 squared. And now we're fully factored. So now remember, we have to treat it like it's an equation. Where is this equal to 0? Well, it's equal to 0 when x is 0. This guy tells me when x is 2. And this guy tells me when x is negative 3. So I have 3 values to put on my number line. So on my number line, I have negative 3, I have 0, and I have 2. And I want to check something in each piece. So I'll use negative 4, negative 1, 1, and 3. Just choosing the easiest values that I can think of. And we're plugging it in to x minus 2, x plus 3 squared to see if we get something positive or negative. So let's start with the negative 4. If I plug in negative 4, I get negative times negative times, we have a negative inside the parentheses, but when I square it, it's positive. Negative times positive is positive. And now let's do the same thing with negative 1. So if I plug in a negative 1 everywhere, I get negative, negative, and again, because I'm squaring and everything, this guy's always going to be positive. Negative times positive is positive. Well, now what if I use positive 1? Erase all those negatives. 1 is positive. 1 minus 2 is negative. 1 plus 3 squared is positive. Positive, negative, positive is negative. And last, let's see what happens when we plug in 3. 3 is positive. 3 minus 2 is positive. 3 plus 3 squared is positive. And all those positives multiplied together is positive. And now we just have to remember what we were solving. What we wanted was this whole polynomial to be greater than or equal to 0. So looking at my number line, I see that I'm greater than or equal to 0 everywhere except for between 0 and 2. And since it's equal to 0, I can include the endpoints. That means this piece here, negative infinity to negative 3 and negative 3 to 0, can just be written as negative infinity to 0, because that negative 3 is included in these intervals. And then I have the interval starting at 2 that we include all the way to infinity. And that is where my inequality is satisfied. Let's do 2 more, but it's really kind of just one more example. And then we'll learn about rational inequalities as well, which is basically the same idea. But so far, the 2 examples that we've had, we've gotten intervals or a union of intervals as our answer. So let's do another example where we have 25x squared minus 10x plus 1 is less than 0. So the first thing we're going to want to do is treat this like an equation. So let's try to factor this. We need to multiply the 25 and add to negative 10. So that's going to be negative 5 and negative 5. So we have 25x squared minus 5x minus 5x plus 1 equals 0. Factor by grouping. I can pull out a 5x, leaving 5x minus 1. And I can pull out a minus 1, which gives me 5x minus 1. So fully factored, I get 5x minus 1 times 5x minus 1. So 5x minus 1 squared is equal to 0. Well, when is this equal to 0? Well, when 5x minus 1 is equal to 0. And that happens when x is 1/5. So my number line's only going to have one value on it this time. So I have x is equal to 1/5. And I want to check something on each side. I would use 0 and 1. Those are the easiest numbers I can think of. So when I plug a 0 in, I get 5 times 0 minus 1 squared. Well, that is negative 1 squared, which is positive. And when I plug in the 1, I get 5 minus 1, which is 4, squared, which is positive. So what was this problem asking us to find? It wanted all the values where our polynomial was less than 0. Well, nowhere. I got positive everywhere. I didn't get negatives anywhere. So what does that mean? That just means there's no solution to this inequality. And that's fine. That happens sometimes. So I have no solution, which I can also write as just a set that has nothing in it. Or you can use the empty set notation, which looks like a 0 with a slash through it. All of those mean the same thing. Now, continuing this example, what if instead of 25x squared minus 10x plus 1 is less than 0, I did less than or equal to 0? All of the work would be the same. It's just the conclusion that's different. This is the exact same problem, I just have an equal to underneath. And that changes things a little bit. Yes, it's still positive in those places, but this 1/5 was where this was equal to 0. So then I would have one single point where it's satisfied when x is 1/5. This example here was just to show you that sometimes you don't get a full interval. Sometimes you just get a point, sometimes you get nothing at all. Those are all possibilities, so you shouldn't be scared if something like that happens. It's a completely normal answer to get. All right, so that is how we do polynomial inequalities. But what about rational inequalities? Our definition. If f of x is a rational function, then f of x less than 0, f of x greater than 0, f of x less than or equal to 0, or f of x greater than or equal to 0 is a rational inequality. So this definition is not even that much different. The only thing that's changed is instead of it being a polynomial, we have a rational function. So that's polynomial divided by polynomial. And the only thing that changes in solving is that instead of just using where our function equals 0 as boundary points on that number line, I also have to include points where my function is undefined. So things that make me divide by 0. Those are also boundary points on the number line. Otherwise, it's exactly the same procedure. So let's start right here. I have 5 minus x over x minus 1 is greater than or equal to -2. And the first thing we want to do is move everything to one side, so we have it with a 0 on one side. So I'm going to add 2 over to the left side. Well, this is kind of a hot mess right now, so I'm going to write it so I have a common denominator. I do that by taking my 2 and multiplying it by x minus 1 over x minus 1. Now I can add across the top to write this as just a rational function greater than or equal to 0. So I will have 5 minus x plus 2 times x minus 1 all over x minus 1 is greater than or equal to 0. Distribute on the top. And then combine your like terms on the top. That will get me x plus 3 over x minus 1 is greater than or equal to 0. And now to finish solving this, I want to figure out where this guy is equal to 0 and also where it's undefined. I can already see where it's undefined. It's undefined at x equals 1. So undefined at x equals 1, so that makes me divide by 0. And the rest of this equals 0 when just the numerator equals 0. You can get there by multiplying both sides by the denominator. So I get x equals -3 as my other boundary point. So on my number line, I need a boundary point for where it equaled 0, and a boundary point where we were undefined. And now I need to check values in each piece of the number line to see if we're positive or negative. I would choose -4, 0, and 2. Again, you can choose any numbers that you want. I just happen to choose the ones I think will be easiest to figure out. So remember what we were using. We had x plus 3 over x minus 1. When I plug in -4, -4 plus 3 over -4 minus 1, my numerator is negative, and my denominator is also negative. A negative divided by a negative, positive. If I do the same thing with 0, plug in 0 for all the x's, my numerator is positive and my denominator is negative. Positive over negative is negative. And now we just have to check for when we have x equals 2. So when x equals 2, I have 2 plus 3 on the top, that's positive. 2 minus 1 on the bottom is positive. Positive over positive is positive. And now we just have to write our answer. We wanted where our function was greater than or equal to 0. So I definitely want these positive intervals. Now is the only dangerous part. Let me write down those intervals. I have -infinity to -3, and I will have a 1 to infinity. But I've purposely left off the parentheses or brackets right now on those endpoints. We have to be careful. This did say equal to. We had greater than or equal to. However, this point will be included. -3 was what made our function equal to 0. But I'm not going to include 1. And the reason for that, my function was not equal to 0 at x equals 1. It was undefined there. So you still use brackets for equal to, but make sure you use parentheses on anything that makes your function undefined. And this would be the answer to the inequality. All right, one last rational example to finish up this video. Let's solve 1 over x plus 4 is greater than or equal to 1 over x plus 2. So again, we start by bringing everything over to one side. And I know a lot of you out there probably are wanting to cross multiply when you see this, but please resist the urge to cross multiply. Since we don't know what x is, we don't know if we would have to flip this inequality sign or not. So don't multiply, instead just subtract one side over to the other side. Now, in order to write this as a rational function, I need a common denominator. I have to multiply the first guy by x plus 2 over x plus 2. And I have to multiply this other guy by x plus 4 over x plus 4. And now they have the same denominator. So rewriting it by subtracting across the numerator, I have x plus 2 minus x minus 4 over x plus 4 and x plus 2. Be very careful when you're subtracting here. This subtraction gets applied to both the x and the 4. That's why we have a -4 up there. Now when I combine my like terms, the x's disappeared. I just have -2 over x plus 4, x plus 2. And there's my inequality. Now, where is this undefined? It's undefined when my denominator is 0, and that happens at x equals -4 and at x equals -2. Where is this equal to 0? Well, if I try to solve that, and I multiply both sides by the denominator, I get -2 equals 0. So that means there's no solution for where it equals 0. So the only points I need on my number line are these values that made this undefined. So on my number line, I use -4 and -2, and I need to check values in each section. I would use -5, -3, and 0. And remember, what we're checking it in is -2 over x plus 4 times x plus 2. If I plug in the -5, well, the top is negative. The bottom, -5 plus 4 is negative, and -5 plus 2 is negative. So I have negative over positive, which is negative overall. Okay, now let's see what happens with -3. I'm going to leave that negative written on the top because that -2 is always going to be negative, no matter what we plug in. So if I plug -3 in for x, my denominator, -3 plus 4 is positive, and -3 plus 2 is negative. So my denominator is negative, but negative over negative makes it positive. Last one to check. If I plug in a 0 for my x's, the numerator is still negative, 0 plus 4 is positive, and 0 plus 2 is positive. So negative over positive is negative. Now this problem, we wanted where it was greater than or equal to 0. So I want this positive section in the middle. So it's all the numbers between -4 and 2. But remember, sorry, -4 and -2. But remember, these two values here were where my function was undefined, not where it was equal to 0. So I need parentheses on this interval because those numbers made me divide by 0. It's not where it was equal to 0. So this will get us our final answer to that problem. So that's all there is to it. That's how you solve polynomial inequalities and rational inequalities. It's not too bad. It's like solving a polynomial equation or rational equation, and then just checking to see if things are positive or negative. If you have any questions, feel free to drop them below, or if you're a current student, you can also email me or come to office hours. And I will see you in our next video.